Alright, total class. Okay, so I grabbed this book. It's a pretty cool book, The How and Why of Mechanical Movements. Just talking about that lever, that compound lever system. There's an actual picture showing one used to weigh trucks. This can be used to weigh trucks up to 75 tons. So, yeah, it's pretty cool. I also wanted to show another picture. This is a pretty amazing pulley system here. I'll just show the picture. So basically, it's like a single pulley, but it like a single cylinder, but it has two different diameters. So imagine you crank this in a way that, let's see if I can describe it. Yeah, like say you lift this, I'm totally blocking the picture. Say you lift this end up and it drops the other end down. Well, this one's a little bit bigger. So say you turn the crank one time. That's going to lift the rope up here a significant amount. That would like lift the mass up a significant amount and drop it down a little bit smaller amount. So the net effect is, you turn that crank around one time, you're applying a force through a fairly large distance, but the amount that you're actually going to lift this, the weight, it depends on the difference in the diameters of the two parts of the cylinders. And if they're not much different, you turn the crank all the way around, you apply a force through a pretty large distance, but it's only going to move up a tiny amount. And so with a device like that, you can make a mechanical advantage of just about anything you want. If you just have a tiny difference between them, that would give you a huge mechanical advantage, because the net effect is it's not going to lift up very much. And there's a more modern kind of example of that right here, which we used to like lift an automobile engine. You can see like on top they've got the two different diameters, but they rotate together. And this one doesn't have a pulley system. You can just pull on the chain to get the same effect. So again, you can create pretty much whatever mechanical advantage you want with a pulley system by just having different diameters. But I wanted to go over one other type of machine, and this is called a hydraulic lift. So I'm going to show kind of a simple thing to start with. So let's say this is just a cross section. You have a device with a very small cylinder here and a larger cylinder here, and you have these movable pistons at each end that are floating on, say, water. So, or let's say oil would probably be more likely used here. So you've got oil here. And let's say we apply a force here. So what we're doing is we're pushing down. Now, fluids like water and oil are virtually incompressible to any significant extent anyways. So if you, if you take, say a gallon of water at the surface of the ocean and bring it to the bottom of the Mariana Trench where the pressure is enormous, the volume of that water would only change by about 3%, I think. So, not even a significant change with that extreme pressure difference. And so we can treat this fluid as being incompressible. And so if we push this cylinder down a distance, let's call this D1. We're pushing this much fluid, whatever is in this portion of the cylinder. This is the volume of fluid that we're pushing over to this end. However, this has a much greater area. Let's say that this cylinder has an area A1. This end has an area A2. And so let's say we have a 1 gallon of fluid here. that could be a significant difference because it's a narrow cylinder. But if you look at this much larger cylinder, if you add a gallon of fluid here, how much are you going to lift up this end? Very little. We'll call it D2, but D2 is going to be much smaller. So how much is D2 exactly? We can use our ideal, but the principle for an ideal machine is that the work is the same. And so what we can say that, let's call this delta V, or let's just call this V1, and this here V2. So let's start by saying V1 equals V2. That means whatever fluid we're displacing on this end is going over here without any compression. So we can start with that. So now the volume on the left side, that's going to be this area times the distance. And over here, we'd have A2 times D2. Should have used radius instead, then we could have R2, D2. But anyways, so yeah, we get this result that A1 D1 equals A2 D2, just because this fluid is incompressible. So let's look at the work that we're applying on the left side, W1, which is equal to W2 because this is an ideal machine. So W1, that would be the applied force times D1, and W2 is, let's call this F2. We'll keep flickering on and off, but we're good so far. And so we can see that let's calculate the mechanical advantage. So that would be the force required without the machine. Like say we put a mass here, we want to lift that up, we'd have to apply a force F2 divided by the force that we're applying, which is Fa. And so F2 over Fa, that would be D1 over D2. And D1 over D2 is A2 over A1. So the mechanical advantage for this hydraulic system is D1 over D2. This is A2 over A1. Now again, we have the same mechanical advantage working against us when it comes to distance. So like say we want to lift, let's look at, let's make up some numbers for these two cylinders. Let's say cylinder 1 has a radius of 10 centimeters. And say R2 has a radius of 3 meters, or 300 centimeters. That's actually kind of big. Let's say 200 centimeters. So that'd be 2 meters. This is a big platform that you could like stand on, or maybe put a car on. So yeah, this you might have seen a hydraulic lift at a gym where they lift up cars. So yeah, R2, let's say 2 meters. That would be big enough to lift up a car. Still probably too big. But the mechanical advantage, or in this case, the ideal mechanical advantage in this situation, well, the area is pi r squared, and so we have pi r2 squared over pi r1 squared. The pi cancels out. So we'd have 20 times 20. 20 squared over 10 squared, or 20 over 10 squared, that's 20 squared. So the ideal mechanical advantage in this case would be 400. So that is a huge mechanical advantage. But that's something that could realistically be built. Now, again, in the real world, there'd be friction to deal with, but So the actual mechanical advantage would be somewhat lower. But yeah, we could design a machine that you could fit in a large room with an ideal mechanical advantage of 400. Now the trade-off, let's say we want to lift this object up 1 meter. That means we'd have to apply a force of through a distance of 400 meters on this end. So again, something has to be done to make that possible. You can't just build this cylinder, 400 meters tall. That'd be a little bit ridiculous. So the way a hydraulic lift would work is you'd have to have a couple levers. And you'd have to have, let's say, a lever here. Or a valve, not a lever. And we'd have to have a reservoir as well, where we could add more fluid. So let's say we have a reservoir with extra fluid here. So what you do is you push down on this end through, however far you can push it down. That would lift this end up a tiny bit. And then if you lift this cylinder up, the fluid's just going to flow right back. So what you do is when you're down at the lowest point here, you close this valve. So if you lift this cylinder again, the fluid can't flow back. And that's why we'd have extra fluid from this reservoir would then flow in to make up the difference. And then you open the valve, push this down. Once it's down as low as it goes, you close the valve. And again, you could have these done automatically so that the act of pushing down opens the valve. And then when you release it, the valve closes on its own. So you can just keep pumping this end up and down. Maybe have a spring here to lift it back up automatically. So you just keep pushing down, and this end just keeps inching up slowly. I'm pretty sure that's how a chair works, like those chairs where you can push on that pedal and lift it up, or like at a barber shop or something. Those kind of chairs. Now, if you're going to lift up a car with something like this, it would be, probably handled electrically instead of mechanically. But again, you could easily lift a car using your own power with one of these machines. Just you applying the force. If you can have a mechanical advantage of 400, you could easily lift up a car. If a car weighs 1,000 pounds, if you divide that by 400, that'd be 2.5 pounds. Even if it only has an efficiency of 50%, you can easily exert a force of 5 pounds. So, these machines can do pretty amazing things. And this is a simple machine, just as, not like a compound thing where you have one lever push another one. So this is a very simple machine that you can use to create a huge mechanical advantage. And so that'll be it for machines. Yeah, I talked about everything in the book. So yeah, that'll be it for this topic.